Good morning. It's my pleasure to break the ice this morning, and I will present you some, let's say, research progress regarding magneto-rheological control of cementitious materials used for 3D printing. I guess you're all aware, and it doesn't matter whether you apply traditional or innovative casting processes, but you're all aware that sometimes you have contradictory requirements for what the fresh concrete should do. Even if you have traditional casting of a wall, first stage it should be flowable for the pumping process, for instance, and then as soon as it is in the formwork, it should be stiffer to reduce formwork pressures, etc. And I think in 3D printing it's even more prominent. So you have the three phases. You have the pumping phase, the extruding phase, and then the phase where you put it in layers where you need the buildability. So you have really contradictory requirements for the rheological properties of your material. Now in Ghent University we developed a new concept which we call active rheology control, and it includes also active stiffening control. If you want to know more details about it, there is an open access book with the title you see. So if you Google that and you go to the website of Taylor and Francis, you can download for free the PDF version of the book. Of course, if you want a hard copy of the book, then you need to buy it. So this is let's say, the result of what we did in the major European project, ERC, European Research Council Advanced Grant Project, which took us 6 years. It was intended to be 5 years, but the pandemic gave us an extra year, so it finally was 6 years. So there we developed different approaches to have active control. And what I mean with active control is once the concrete is already flowing, you give an external signal in some way to activate some particles or polymers in your concrete that give a certain response, and you change your rheology. And as I have a couple of minutes extra, I understood, so maybe I can show. On the left side, we have here what we call the polymer route, and that's not the topic of today, but as I have some minutes extra, I can show you, for instance. One of the things we did is redox responsive superplasticizers, so it's some kind of switchable superplasticizers that have the normal backbone, normal side chain, but we have also special side chains which we can trigger. And there we can induce, by triggering in this way, some positive charge, counteracting some negative charges of the backbone. And this is like playing with the adsorption capacity of the superplasticizer to the cement grain. So we can have a slight control on how much of the superplast is adsorbed on the cement grain, and this is leading to a small adjustment of the flowability of the concrete. Don't ask me after my lecture, I want this on my construction site, please give me a few liters of that. No, I cannot give you. It's a lab scale proof of concept at this stage. So in the small scale rheometer level and small scale level, we have shown that it works. Of course, we are now having upscaling studies, and they are quite challenging, of course, but we are upscaling. So that's the polymer route. You can read more of that in the book if you want. Today I will focus on what we call the particles route. We use nanoparticles or microparticles, and one option is there to go for magneto control. So we have magneto-responsive particles that we incorporate in our systems, and we try to activate that in some way to provoke changes in the rheological behavior. Actually, it's more or less the same principles as magneto-rheological fluids, as you can find in mechanical engineering, for instance. We might go in two ways. So if you have constant magnetic fields, particles might form chains and invoke some stiffening inside the material. It becomes stiffener. And that will be, of course, relevant for the 3D printing, which I will talk about later on. But you can also have, a changing magnetic field. Okay, now the video is working again. So if you have a changing polarity of your magnetic field, north and south poles are changing, then the particles might flip over, and due to their movement, they might give some, let's say, disturbance of the internal structure and lead to more flowable material. So we have tested this, for instance, in rheometers. So here you have a situation with a constant magnetic field. Here you have the reference and the ones with the magnetic particles, but without magnetic field. So 0 Tesla means no magnetic field. And you see the increase in storage modulus. So it's small angle oscillatory shear that we perform here. And once we apply a magnetic field, this is a quite strong one, 0.5 Tesla. You see that, whoops, the increase in stiffening rate is really enormous. You can get a very fast stiffening rate. So that's the active stiffening control, which will come back in the 3D printing in the further slides. But you can go the other way. So the same kind of test, so storage modulus, a small angle oscillatory shear, but at some timings, at some intervals, we give a short magnetic pulse. We have a short time a magnetic field, and then we trigger some movement of the particles. And the movement of the particles is disturbing the internal structuration, is removing the structure, and thus reducing the modulus. So you see, you have this pulsed magnetic field, structure is going down, and as soon as the field, as the normal situation is reinstated, you have an increase again. Another pulse, you go down again. So with this, you can play and have a control. So if you combine the two options, basically you could say that you can control your storage modulus in the shaded area, depending on what you are doing with your magnetic field, either constant or either pulsed magnetic field. So those are the main principles, let's say. So let's now move to 3D printing, 3D concrete printing. First, a few general slides. A couple of years ago, I think it's already 6-7 years ago, we were involved in the printing of the first 3D concrete printed house, 2-story house in Belgium. We were the scientific partner there. I think the result is nice. In our lab, we also perform studies on topological optimization. For instance, you see here a bridge deck that has been printed in our laboratory by students, and that is showing what we are doing. So here you see a setup of our large-scale robot printing. We have different setups, but this is the largest scale we can go. Actually, you see there column printing. Be careful, it's accelerated here at double speed. Normally it's half of the speed. But we can go fast. We can print a column of 3 meters in 10 minutes. We developed special techniques for that, special materials. The special technique, for instance, is like what we call the twin pipe pumping. We subdivide our material, our finer material, in 2 streams. We bring them together to a static mixer. The 2 streams in itself have a very long open time, basically indefinitely, but once they join in the static mixer, they are flash accelerated and going very fast. Let's say in 10 minutes we can build a column of 3 minutes, and we can print with very large overhang, over openings, things like that. You see other topics that we are working on. That also includes, for instance, which is not mentioned here, a printing of alkali activated materials. That's also one option that we can do with the twin pumping system. Okay, let's now focus to application of this magneto control in 3D printing. The principle is, with the magnetic control, we want to have active stiffening as soon as the material is coming out of the nozzle, at the end of the nozzle phase. So a first study we did was some kind of simulation in a rheometer. So not in a printer, but in a rheometer, a plate rheometer, so a 1 millimeter gap. And we did some pre-shearing at high shear rate, representing the mixing phase in the printing process. Then we have a period of 60 seconds with a lower shearing, which is simulating more or less pumping and extruding. And then at the end of that, which is considered to simulate the end of extrusion and building of the layers, we did a small angle oscillator shear times sweep test to see how the modulus is evolving. So we did several tests with that, with our material. In some of the tests, we had a magnetic pulse here at the end of the extruding phase. So 1 second magnetic pulse, which is very short. You might wonder how this could give so much effect, but that's what we did. So here you see a result for a specific, for one of the mixtures. So we have the, let's say, simulation of the mixing phase, so the pre-shearing in the rheometer. Then we have the lower shear rate period in our rheometer that is more like representing pumping and extruding. And then we can have a 1 second magnetic pulse, and you see the difference, what is happening here. So after this, you need to look to the right axis here, there it's storage modulus. So in the normal situation without magnetic field, this is the evolution of the storage modulus. Upon the magnetic pulsed situation, 1 second only, you see a tremendous effect, and the modulus is really increasing very fast. Okay, this is in a small scale setup at rheometer level. What is happening there? Okay, in the beginning you have your material with the magneto-responsive particles distributed uniformly. As soon as you apply your magnetic field, chains are formed, and when you release the magnetic field, okay, the chains are released somewhat. It depends on the remnant magnetization of your particles, in how far you keep the change or not. So that is what's happening, and the importance of remnant magnetization is shown here. Here we see a similar kind of test, but two different mixtures, and the difference is the magnetic nanoparticles or magneto-responsive nanoparticles. We have 1 and 2, and the number 1, which is the blue one, is a higher remnant magnetization. That's given in the text here. So if you remove the magnetic field, there is some remaining magnetization, which is higher in the case of particle type 1. And you see that the values are higher here, the storage modulus values in the case of higher reminiscence of the material. Okay, we want now to upscale this kind of test so that we can do, for instance, a squeeze flow test, because if you print layers, the first layer is a little bit squeezed by the next layer, so we wanted to simulate that. So for that we needed a system where we have a higher volume of sample here in a cup, and of course we need a system to apply the magnetic field, because we are no longer in our plate-plate geometry with the 1 millimeter gap where the rheometer has the facilities to do so. So we built it, or our student developed and designed a new setup that can come along the cup, and where very strong magnets, permanent magnets, can be situated. So this is the cup here, and there the new elements, which can then by step motors be operated to be moved towards the cup and then removed, so that we can very strictly control the magnetization time. And once it is removed, we can check the effect, and that's what we do. So then we come to this situation. The sample is in a plastic mold. Of course, it needs to be magnetic mold. Mold can be removed, and then you have the top plate of the rheometer, non-magnetic in this case, and then we do the squeeze flow test to see how the material behaves, simulating the effect of subsequent layers compressing the previous layer. And then we see some results here. I'm not going into detail, but what we see is we have different curves for, let's say, squeeze flow tests with different load levels, 1 Newton, 1.5 Newton, 2 Newton. And then you see different curves. The top curve is the displacement here when no magnetic field was applied, and then the lower displacement is the result for the case where the magnetic field has been applied. So we see the effect of the magnetic field also on the deformation of the layers. We did some electron microscopy where we saw indeed that we had some chain formation in the case where the magnetic field was applied, contrary to the standard reference case. Now I have better results. My student showed me last week some images obtained with computed microtomography, and we even have three-dimensional images that we can rotate, and there you clearly see the chain formation of the particles. It's very nice to see, but it came too late to be included in my presentation, so maybe next time. Yeah? So what happens as soon as you apply the magnetic field, you get this chain formation which is remaining at least partly after the application of the magnetic field. Of course, we can check the influence of water-cement ratio. If you have a more flowable material, then the chain formation is more easy, of course, than in a more stiff system. So that's, of course, logic, but we check that also in this test. So let's summarize a little bit this research in progress. Let's say the next step would be upscaling to the 3D printer, and we are preparing this setup there to do magnetization around the nozzle in the large-scale robot setup. So a preliminary investigation was performed regarding application of inline magnetic field in the case of 3D concrete printing with a new setup. And yeah, I didn't mention, but in the setup we applied magnetic field of only 0.1 Tesla, which is not that large, and we saw the effects. So we had clear proof that clusters and alignment of particles was obtained, and important due to the remnant magnetization, the structures at least partly remained after removing of these magnetic fields. And we saw the effect also under this squeeze flow test. Now, the water-cement ratio is an important, or let's say the flowability of your material is important. If it's very flowable, your chains are easily formed, but they are also more easily destroyed afterwards. So that's a trade-off that you have. If your material is too stiff from the beginning, then the chain formation is also quite complicated. And as I said, further research is ongoing to further upscaling and for the situation of real 3D robot printing with our robot setup. So with this, I thank you for your attention, and you see the members of the SmartCast team who developed the active rheology control and active stiffening control that we are now bringing into practice for the 3D printing. Thank you very much.
Thank you for a very interesting presentation. That's very, very interesting. So I wonder, we have enough time. I want the audience to ask some questions. If you do, please go to the microphone.
Thank you very much for a very interesting presentation. So would you call this effect as an extra flocculation, the Magneto-Rheological effect? And have you tried to characterize by testing, by rheological testing, how much you need to break this?
Yeah. Well,
and can you return back to a non-flocculated state?
Thanks for the interesting question. All of this, or large part of this, has been done, not all, large part of this has been done in the framework of the SmartCast project and has been published in the book. We indeed consider, let's say, the effect of the magnetic field on what happens inside as some kind of structural buildup, you could call it thixotropy, that was really triggered by our signals. Starting from already available published models for thixotropy, we even extended those thixotropy models, or one of those models, to include the effect of the external field. So in this way, we can quantify in some way what the effect of the magnetic field is in terms of structural buildup internally. Of course, this needs further validation because the model has been extended based on small-scale experiments. It needs further validation, but that was a first step coming towards the thing you wanted to see, something quantifiable and have in advance a good estimate of what your system would need or what it would be able to do.
Thank you very much.
Yeah, very good presentation, Geert.
Thank you, sir.
You compared the storage modulus, the control, with the one where you applied the magnetic field. Would it be interesting to compare the storage modulus of control with normal thixotropic agents such as metacellulose or nanoclay and
Yes.
see how the magnetic...
Yes, that's a very relevant question, and we do have results showing that. Of course, this was not the topic of today, but with our triggered control, we can do better than with, for instance, nanoclay. Yeah. So it has an extra compared to the natural system. Plus, it is on demand, while the nanoclay is not really on demand. Yeah.
Hello, many thanks for your presentation.
Thank you.
One question, all the measurements you did in cement paste, right? Or like the rheological ones?
Yes, what I showed was in cement paste, but in the meantime we have also upscaling studies at mortar level, and paper has just been accepted. It will be published in the coming weeks. So we showed that it's also working in mortars.
And
So the
effect
next
is-
step is concrete, of course.
The
yeah.
effect is similar, or do you have like a lower effect
In
mortars?
principle, the effect is similar, but of course, due to the presence of sand particles, you diminish a little bit the effect. Now there, the interesting idea is some sand particles also can be magnetizable.
Exactly.
And if you use those ones, then of course the effect is marvelous. Yeah.
Okay, thank you.
Thank you very much for this very nice presentation and very nice walk to walk that is outside of the box. So I really like that. My question: you show clusters and nanoparticle clusters. So I'm wondering the effect of these clusters on the property of the material, and then do you see differences between the different layers because in terms of the clustering? So that's one aspect of the questions. But then trying to think, can we use this approach to disperse nanoparticles actually, or to orient some of the fibers maybe that we put
Yeah.
in? So I have a lot of follow-up questions on this.
So with the clustering, you mean the initial clustering
Yeah.
after mixing immediately? Because
well,
that
after
also,
mixing and then when you apply the field, because
Yeah.
you're creating this clustering. So I'm wondering what
Yeah.
is the effect then after, because they are going to remain there. They are
Yeah.
clusters. So
Yes, of course, with nanoparticles, indeed, you have the risk of having clusters even after mixing. So you need very intense mixing process to limit the clusters. I'm not saying that you can really avoid all of the clusters.
No.
That's not possible. But we check that, and we can really have a minimal amount of clusters from the beginning. Now, if you apply the magnetic field, of course, we induce clustering. But it's more, let's say, fibrous clusters. It's more an alignment of clusters, which helps us to bring the stiffness in the material. And after removing of the field due to the remnant magnetization, it's more or less remaining like that, although, well, not fully. It's partly going back again. Now, can you use this technique to distribute the particles? I don't think so. At least we've never seen an effect that by applying fields in some way we distribute the particles. No, it's always forming clusters that you achieve. Yeah, but even there you have to be careful how long you do the cycles, etc., because you have the flip over, but at the same time you have magnetic forces bringing them together. So I don't see how this will be helpful in dispersing the particles now. And then you mentioned the fibers. That's also an interesting idea that we were working on. So, of course, if you have steel fibers in your system and you apply magnetic fields, the steel fibers will orient according to the field lines. That's another work in progress that we are doing, and you could even try to do it on the printed layers. It's complicated, but in principle, it has an effect. Yeah.
Have you looked at the effect of that clustering on the filament properties?
No, in those details we didn't go so far. Sorry.
Thank you. Thank you.
Thank you.
Sure, we
Yeah, we
have
have few more minutes,
more,
yeah.
yeah, we still have time.
You take away from time from his
Oh, yes. Well, so I will start
You
most
were
probably.
relaxed.
Yes, so excellent presentation and very innovative approach. Really, I think you were the first who brought it up, I think, at such a detail. And I remember like your first presentation at Gordon conference before pandemic.
Ventura, yeah.
So it was, it's really, I think, a very stimulating study for all of us. My question is, I think this is what maybe we discussed in the past, but the potential effect on hydration.
Mm-hmm.
Do you think we can really modify it was one of the ideas we were thinking about, can we modify the hydration processes by applying magnetic field and not only to have like early age properties, but effect on hydration and maybe formation of the different type of hydration products?
Just by the effect of magnetic field, you mean?
By magnetic field, by initial, again, we are not talking about 24 hours magnetic field.
No.
We talk about like fresh properties, modifying fresh properties within, I don't know.
I have a student working on that, really on the fundamental level of the hydration process in the very first minutes and hours, an effect of magnetic fields, even strong magnetic fields. Theoretically, you could have some influence, a very minor one, but there could be some influence. But doing experiments, etc., we've never seen any noticeable change at the level that we are interested in as engineers, like heat of hydration development or strength development or whatever.
A product of hydration.
Products of hydration, also no differences.
So chemistry is still there.
If there is a difference, we didn't notice up to now. Now, you can find in literature some papers where they first magnetize the water, take the water at the magnetic environment, and then make concrete and claim to have some observations.
Yeah, for example.
But this is, to my feeling, not possible. Less than 1 second after you remove the water from the magnetic environment, it's normal water again. So forget about that. And if you check these papers and you check the variation in the results and you do statistical test, you will come to the conclusion that there is no significant difference. But yet the paper was published, showing that magnetizing your water first has the effect. So be careful sometimes with papers. But we up to now did not see any noticeable effect on hydration.
That's a good point. Okay, thank you.
Thank you.
Anyone else have any questions? Please go to the microphone.
Hi. Thank you for the presentation. My question is about the magnetic particles that you are using. You are using nanoparticles and it's 3%, I guess. How cost effective they are to implement in the site?
Not. At this moment, they are not cost effective, but I'm doing research. I don't care about cost at this moment. But the smarter thing, if you care about costs and reusing materials, is to go for some kind of sand particles that are wasted anyway sometimes, but do have some magnetizable properties. With the, let's say, specially produced particles at very expensive cost, we try to show the principles under very well controlled conditions, but I think later in reality we have to go for other materials than that.
And why are you using nanomaterials instead of micro ones?
Oh, we use nano and micro,
Okay.
and for the sand even milli.
So probably it will be cheaper if you use micro ones, right?
Yes, that's already way cheaper, and then the sand, of course, that's very cheap.
Thank you.
So for that question, what's the concentration you use in the dosage?
For the nanoparticles, I think it's typically 2%, 3% in volume. If you use the sand particles, maybe they are not so magnetizable as the finer nanoparticles, but of course there will be a larger volume, and the effect will be more prominent by volume.
Have you looked at the interlayer property?
Not in the case of magnetically controlled printing, not yet. First we need to upscale our control to the 3D printer, and then we can go for that study. We did interlayer studies in normal printing situations, but not with the magnetic control.
Other questions from the audience? We still have a little bit of time. So,
I should have known before, I deleted some slides.
you
You had more time, but you also had more questions.
Yeah, but that's good, yeah.
Very interesting work and very innovative. I have one question. So Costa asked you if it had any chemical effect on the hydration products, but does it have any physical effect? Does it change the pore distribution or the structures themselves, the packing densities or something that changes it, that has a stiffness effect?
The structure, yes. I mean, it's induced change of structure that we want to see. The interesting question is the pore structure. Is that changing? That we didn't test up to now, and that's certainly a to-do on our list, yes.
Oh,
thank you for the
thank you.
question.
We want to thank the
My pleasure.